History is supposed to be a straight line connecting us in the present to the distant past, helping us to link past events together. However, scientists have just discovered there's a yawning gap where huge parts of the universe's history are missing. Why is this happening, and what does it mean for our existence today? Join us in this video as we dive into why a huge chunk of the universe is missing. Humans have a deep connection to the past, which is why history is a big deal to us. As a result, scientists devote a lot of time and resources to finding out what happened in the past and how the events of the past shape our present realities. Sometimes, however, what they discover about the past is shocking, especially when they come across parts of the past that are lost to them and they can't fathom it. Some of such cases are the huge pieces of the universe's history that they can't use any modern methods to account for. Interestingly, the Earth itself is missing some parts of its history, and this is one of the deepest mysteries ever known to us. It is like your high school teacher wiping off the board and losing all the information on it to eternity, never to be recovered. This is known as the Great Unconformity. Using clues from the Great Unconformity, scientists are now trying to unravel the mysteries of the huge missing pieces of the universe. The Great Unconformity, or GU, is a time gap in the geological record that ranges between 100 million and 1 billion years and occurs in various rock sections around the world. What happened was researchers discovered chemical evidence in rocks indicating that the GU formed near the end of the Precambrian period, between 850 and 680 million years ago. And on a much grander scale, the cosmic microwave background cold spot, or CMB cold spot, is a huge gap in the universe's history that scientists are trying to explain with the different interesting theories. You see, significant events in time and space leave indelible imprints on the universe. The Big Bang, the cataclysmic event that gave rise to our universe 14 billion years ago, has undoubtedly left its imprint on everything we see today. The most lasting imprint, however, is CMB, the primordial microwave radiation that fills the universe. Our once newborn universe was a teeming hot, dense plasma made up of nuclei, electrons, and photons for the first few 100,000 years. However, by 380,000 years, the universe had expanded and cooled to temperatures below 3,000 Kelvin, allowing neutral atoms, including atomic hydrogen, to form. And light finally abounds the universe due to the absence of free electrons, and the CMB emerges. As a result, this relic radiation is a perfect record of our universe in its infancy. And because of the expansion of the universe, the CMB has been stretched to its current microwave wavelength and cooled to a temperature of only 2.7 Kelvin. At first glance, the CMB appears to have a near-perfect black body spectrum, that is, a uniform temperature and scales of around 10 to 5 Kelvin. However, at microkelvin scales, we begin to see temperature variations in the form of hot and cold patches. Small quantum density fluctuations that occurred when the universe was young meant that matter was not evenly distributed. Instead, some regions of the universe are more densely packed than others, resulting in the large-scale cosmic web network of matter that we see today. Because of this difference, light traveling through a densely populated region has to overcome a stronger gravitational pull and thus appears redshifted, whereas light traveling through a less dense region appears blue-shifted. This change in wavelength of CMB photons is reflected as temperature variations on the K-scale. In other words, there is a relationship between temperature and isotropies in the CMB and the large-scale structure of the universe. The gravitational effect that causes the CMB's large scale anisotropy is known as the Sachs-Wolf effect, and it is divided into two parts. The ordinary Sachs-Wolf effect, which only applies to the early universe and describes the gravitational redshift of light from the last scattering surface, is one example. The integrated Sachs-Wolf, or ISW effect, on the other hand, is based on the effects of changing gravitational potentials due to matter density variations on CMB photons. The primordial fluctuations in the CMB provide strong support for the theory of cosmic inflation, which cosmologists believe occurred when our universe was only 10 to the power of minus 35 seconds old. These fluctuations, together with gravitational lensing, the bending of light caused by matter as predicted by Albert Einstein, and the Sunyaev-Zeldovich effect, which is the distortion of energy in CMB photons caused by high-energy electrons in the galaxy clusters they pass through, allow scientists to calculate the relative abundance of dark matter and dark energy in the universe. The scientific community loves CMB because it's provided them with vast amounts of data since it was predicted by cosmologists Ralph Alpha and Robert Herman in the late 1940s, and then experimentally detected by physicist Arno Penzias and radio astronomer Robert Wilson in 1964. However, it has revealed some perplexing mysteries and anomalies, such as a significant discrepancy in the CMB observed in the two opposite hemispheres of the sky. The most intriguing mystery concerns a large and unusually cold patch on the CMB that spans more than 1 billion light-years. The CMB cold spot, first observed by NASA's Wilkinson Microwave Anisotropy Probe and later confirmed by the European Space Agency's Planck satellite, is about 70 microkelvin colder than the average CMB temperature and appears in the southern celestial hemisphere. While the cold spot could have formed as a result of the primordial density fluctuations that cause the rest of the CMB's temperature anisotropies, this is unlikely. These anisotropies have a Gaussian distribution which allows for small but not large variations. However, in some locations, the cold spot is nearly 150 Kelvin colder than the mean CMB temperature, far exceeding what would be expected from a Gaussian distribution. Furthermore, the radius of the cold spot is about 5 degrees, whereas the largest fluctuations in the primordial CMB temperature occur on angular scales of about 1 degree, making it even more out of place. It should come as no surprise then that researchers all over the world have proposed a variety of theories about the CMB cold spot, and numerous studies have been conducted to uncover its origins. Some early theories proposed that the cold spot was simply foreground contamination in the form of galactic dust and synchrotron radiation from within the Milky Way, or that it was caused by unusual celestial objects. However, observations by the NRAO VLA Sky Survey (NVSS), the 2-micron All-Sky Survey (2MASS), and the Sloan Digital Sky Survey (SDSS), as well as detailed Hubble Space Telescope images, revealed no such objects. Because of the large-scale structure of the universe, one promising explanation for the phenomenon is there exists a vast cosmic supervoid between us and the cold spot. While galaxies continue to exist within voids, their matter density is much lower, 1/10 of the average, than in other parts of the universe. On the other hand, the universe contains superclusters, which are large regions with many more galaxies than normal. If a supervoid exists in the direction of the CMB cold spot, the late-time ISW effect could be a promising explanation. Scientists from the University of Minnesota announced they had discovered a supervoid in the region owing to a significant drop in extragalactic brightness and radio source count in the region, as seen in the NVSS radio catalog. However, a follow-up study conducted by Kendrick Smith of the University of Cambridge and Dragan Hutterer of the University of Michigan found no statistically significant evidence for the aforementioned dips in MVSS maps, ruling out the existence of a supervoid. And yet again, another study led by Seshadri Nadatha of the University of Helsinki found that the proposed super ISW void's impact on the CMB is insufficient to explain the cold spot. According to the Helsinki researchers, in order to see the required photon cooling via the ISW, the supervoid would have to be so massive and empty that its very existence would contradict the standard model of cosmology for our universe, known as the CDM. According to this model, the universe is governed by the competing forces of dark matter. Dark matter's gravitational pull opposes the accelerated expanding force of dark energy. Any structure capable of explaining the cold spot would be an anomaly in and of itself. Separately, a team of astronomers led by Istvan Zapudi claimed to have discovered a rare supervoid in the region measuring nearly 1.8 billion light-years across. Zapudi described it at the time as the largest individual structure ever identified by humanity. The team surveyed relatively nearby galaxies that lay within the cold spot's boundaries using optical observations from Hawaii's Pan-STARRS 1 telescope and infrared data from NASA's Wide Field Survey Explorer 2 mass catalog and discovered the supervoid. The void is only 3 billion light-years away from us, which may explain why it was missed in previous searches that focused on the distant early universe. Despite its discovery, the researchers discovered that even this large supervoid does not fully account for the temperature drop of the CMB cold spot, as the cooling ISW effect is only 20 K. Due to a variation of the integrated Sachs-Wolf effect known as the late-time ISW effect, both supervoids and superclusters have a significant impact on CMB photons. CMB photons passing through superclusters, gravitational valleys, gain potential energy and thus heat up as they roll into the valley. All else being equal, the photon should expend this energy as it climbs back out of the valley after leaving the supercluster. But not everything is equal, because dark energy, which causes the accelerated expansion of our universe, enters the picture. Dark energy stretches the valley somewhat, flattening it in the time it takes the photon to travel across the supercluster, so the exiting photon doesn't require all of the extra potential energy to climb back out. As a result, the CMB light retains some of the gained heat. Similarly, supervoids are considered gravitational hills. The CMB photons lose more energy entering a void and climbing uphill than they gain rolling downhill, leaving the now somewhat larger void. This energy loss chills the photons. If a supervoid exists in the direction of the CMB cold spot, the ISW effect could be a promising explanation. In an attempt to test Zapudi's discovery, a study by Roari Mackenzie at the University of Durham used spectroscopic data from the 2DF-VST Atlas Cold Spot Redshift 2CSZ survey at the Anglo-Australian Telescope in New South Wales to study the redshift of galaxies in the line of sight to the cold spot. The researchers then performed the same measurements along a different line of sight as a control for their work. Mackenzie's team discovered 3 voids and a possible 4th void beyond 3 billion light-years. Despite the fact that no single void was as large as Zapudi's supervoid, the 4 combined showed an ISW cooling effect of 31 K, still insufficient to explain the cold spot. And unfortunately, the researchers discovered a similar density of voids along the control line, leading them to conclude that voids are not the solution. Instead, they conclude that the cold spot was most likely caused by primordial density fluctuations. As things stand, the presence of Zapudi's supervoid is difficult to explain in the standard CDM, while simulations show that a random non-Gaussian quantum fluctuation in the CBM has a 1 in 50 chance of spawning the cold spot. Another possibility for the CMB cold spot is the unusual motion of galaxies in the region as a result of extreme gravitational effects. This could be similar to the effects observed due to phenomena like the Great Attractor, which is an apparent gravitational anomaly at the center of the local Laniakea supercluster, within which our Milky Way galaxy is located, caused by an enormous concentration of mass, and the related dipole repeller, which is a center of effective gravitational repulsion in the large-scale flow of galaxies in our local group, caused by the likely presence of a large supervoid. Both have their own imprints on the CMB dipole, but no such unusual structures have been observed in the CMB cold spot area or surrounding regions so far. A study published by Qi Guo and colleagues at the Chinese Academy of Sciences discovered 19 dwarf galaxies that are dark matter deficient, which is surprising given these small galaxies are typically dominated by dark matter. 14 of these galaxies are isolated and not satellite galaxies to larger ones like ours. implying that their lack of dark matter was not caused by interactions with larger or other dwarf galaxies. These low dark matter dwarf galaxies may have an impact on the results of other ISW studies, which are all influenced by dark matter. It will be interesting to see if this behavior is shared by a significant number of galaxies in the CMB cold spot region. Perhaps the answer to the CMB cold spot lies within inflation theory itself, rather than beyond it. It's possible that during our universe's infancy, a local patch of the universe experienced a longer period of inflation, resulting in the formation of a cold spot in that region. Yi Wang of the Hong Kong University of Science and Technology and Yin Jae Ma of South Africa's University of KwaZulu-Natal proposed a feature-scattering inflationary mechanism that predicted localized cold spots and not hot ones. However, if we look at other phenomena such as the effect of such anomalies on density perturbations and the evolution of stars and galaxies in that region, questions about the validity of such theories will arise. As researchers try to figure out which explanation is correct for the cold spot, it's critical to keep other cosmological observations in mind, such as observations of Type 1a supernovae, baryonic acoustic oscillations, and the overall CMB observations in mind. It has also recently been proposed that gravitational waves produced by the merger of heavy objects, such as neutron stars, could be used to make a more accurate measurement of the Hubble constant. With some variations in the values of the measured cosmological parameters, these observations support CDM, and any workable solution must agree with them. Alternatives to the standard model, on the other hand, will be crucial in investigating anomalies like the cold spot. Eleonora Di Valentino of the University of Manchester and colleagues, for example, carefully examined the Planck 2018 CMB data in a study, and their findings challenge our standard CDM assumption of a flat universe. Their findings point to a closed universe which contradicts our current assumptions and departs from our conventional understanding of inflation theory. While their findings were inconclusive, this issue clearly warrants further investigation. And in the absence of a clear explanation for the CMB cold spot, a more unusual and far-fetched possibility has been proposed. The cold spot could be evidence of a collision between our universe and a parallel universe. This is consistent with the multiverse theory, which holds that our universe is one of many that occasionally collide and interact with one another. Parallel universes could have interacted with ours before they were separated by cosmic inflation, and those interactions would have left an imprint on the CMB. However, extraordinary claims like this one necessitate extraordinary evidence that is consistent with other cosmological observations. As suggested by Tom Shanks of Durham University's Center for Extragalactic Astronomy, such a collision between universes should produce an identifiable polarization signal in the cold spot. In addition, the Planck team's most recent results included a deeper examination of the polarization of CMB radiation, which is almost completely independent of its temperature profile, in order to better understand the nature of anomalies like the cold spot. Planck's multi-frequency data are intended to eliminate foreground sources of microwave emission in our galaxy, such as gas and dust. Despite careful examination, the Planck team found no evidence of anomalies in the polarization maps. According to the team, the latest findings neither confirm nor deny the nature of anomalies such as the cold spot, leaving many possibilities open. Improving our understanding of cosmological parameters will allow us to provide better explanations for unusual phenomena such as the cold spot. We need new data from sensitive telescopes like the Meerkat Array, as well as upcoming facilities like the Giant Magellan Telescope and the Square Kilometre Array to do this. To gain a better understanding of how the ISW effect works, we must also better understand the nature of dark energy and how it affects the evolution of our universe. Scientists, however, are moving closer to understanding the cold spot phenomenon. They use the data from the Dark Energy Survey to confirm the existence of the Eridanus supervoid, one of the largest known to humanity, as reported in a paper published recently. This previously hypothesized but now confirmed void in the cosmic web could be a possible cause of the CMB anomaly. The cosmic web is made up of galaxies, clusters, and superclusters. They are drawn together by gravity's attractive force and accelerated apart by the repulsive force of dark energy, a mysterious, unfathomable phenomenon. There are voids between these clusters of galaxies, vast regions of space with fewer galaxies and thus less ordinary matter and dark matter than exists within the galaxy clusters. The supervoid in the constellation Eridanus is one of the largest structures known to humanity. It is a massive, elongated, cigar-shaped void in the cosmic web that is about 1.8 billion light-years wide and has been observed to contain about 30% less matter than the surrounding galactic region. Its center is 2 billion light-years away from Earth, making it the dominant underdensity of matter in our galaxy. Using dark energy survey data, scientists created a map of dark matter in the same direction as the CMB cold spot by observing the effect of gravitational lensing. It is a phenomenon that occurs when the gravitational influence of dark matter warps the path of light. This dark matter map is the largest ever created. They mapped dark matter over a quarter of the southern hemisphere. Previously, scientists counted the number of galaxies visible in the region of the CMB cold spot and discovered an underdensity of galaxies in that region. According to the new map, there is a matching underdensity of invisible dark matter. The Dark Energy Survey is a global effort to understand better the role of dark energy in the acceleration of the universe. It includes 300 scientists from 25 institutions spread across 7 countries. The Dark Energy Survey uses a 570-megapixel digital camera called the D-CAM to document hundreds of millions of galaxies, supernovae, and patterns in the cosmic web. The Fermi National Accelerator Laboratory of the United States Department of Energy oversaw the design and integration of this camera's components. They were thinking many years ago, at least a decade and a half ago, how would voids affect the current acceleration of the universe? At the largest scales of the universe, gravitational forces compete with the expansion of the universe caused by dark energy, deepening some of the voids between galactic clusters. Photons or light particles enter a void before it begins to deepen and leave it after it has deepened. The integrated Sachs-Wolf effect indicates that there is a net energy loss in that journey. Photons gain energy when they fall into a potential well, and they lose energy when they come out. This is known as gravitational redshift. Although the new finding confirms that the Eridanus supervoid is massive, it doesn't explain the discrepancy between the predictions of the current standard cosmological model used to predict the behavior of dark energy, known as the lambda cold dark matter model, and the observed change in temperature in the cold spot that can be attributed to the supervoid's effect on photons from the CMB. Having the coincidence of these two individually rare structures in the cosmic web and in the CMB is basically insufficient to prove causality with the scientific standard. It is sufficiently novel in the long history of the CMB cold spot problem that after this people will be certain that there is a supervoid, which is a good thing because some people have debated that. In short, there are 2 ways to look at this problem. Either the lambda CDM model is correct and the CMB cold spot is an extreme anomaly that just happens to be in front of a massive supervoid, or the lambda CDM model is incorrect and the integrated Sachs-Wolf effect is stronger in supervoids than expected. The latter would imply that dark energy has a greater influence on the universe and that cosmic expansion is possibly accelerating. Surprisingly, evidence from other more distant supervoids supports this possibility. Furthermore, the Dark Energy Survey team discovered that the Eridanus supervoid lensing signal is slightly weaker than expected. The problem is that typical alternative models cannot explain this discrepancy either. If true, it could mean that we don't understand something fundamental about dark energy. And another period in the universe's history that scientists cannot explain is the Dark Ages. This dark age of the universe, which began about 400,000 years after the Big Bang and lasted hundreds of millions of years, marked the last time when empty space truly was empty. No planets, suns, galaxies, or life, just a fog of hydrogen atoms forged by the Big Bang and left to slosh through the darkness. Today, telescopes all over the world are attempting to catch a glimpse of that primal hydrogen in order to pinpoint the moment where the Dark Ages ended and the first galaxies formed. While those ancient atoms remain elusive, a team of researchers in Australia's outback may have come closer than ever before to discovering them. The energy coursing through the early universe was so powerful that it ripped electrons from every atom, giving them a positive charge. The first of these atoms was the positively charged hydrogen ion. The universe cooled and expanded enough over hundreds of thousands of years for these hydrogen ions to regain their electrons and become neutral once more. These neutral hydrogen atoms are thought to have dominated the cosmic dark ages, and eventually when enough of them clumped together to form the first stars, energy radiated from those stars re-ionized the atoms. Neutral hydrogen emits radiation with a wavelength of 21 centimeters, but as the universe has expanded over the past 12 billion years, those wavelengths have also stretched out. The wavelength of neutral hydrogen has stretched to about 2 meters, according to the authors in the new study, and this is the signal they search for using the MWA. The issue is that many sources, both artificial and celestial, emit at the same wavelength. All of these other sources are many orders of magnitude stronger than the signal we're attempting to detect. Even an FM radio signal reflected off an airplane flying above the telescope is enough to contaminate the data. So scientists developed a set of equations to identify and eliminate contaminants in their observations. The researchers determined that every trace of 2-meter emissions they found came from somewhere other than the neutral hydrogen they were looking for after taking over 1,200 radio wave snapshots of the sky. While the prized atomic signal remains undiscovered, the new research narrows the scope of future searches for neutral hydrogen. These findings, according to the researchers, make a strong case that the MWA experiments are leading this hunt in the right direction. With more research, the last relics of the cosmic dark ages could be discovered. What do you think about the origin of the universe? Let's hear your thoughts in the comments section below.